Hello and welcome to this video on iterated integrals and polar coordinates. So iterated integrals and polar coordinates. In a previous lesson, in a previous video, we saw iterated integrals with the variables x and y. Iterated integrals can be calculated in polar coordinates with the variables r and theta. So let's take a look at example 1. So in example 1, I have the integral from pi over 6 to pi over 3, the integral from 1 to 2 of 1 plus 3 cosine theta dr d theta. So integrating with respect to r, you'll notice this function here doesn't have any r's in it, so I can treat this as if it's just a single constant, 1 plus 3 cosine theta. So that means it's going to be this constant times r. So I get 1 plus 3 cosine theta times r, and then I have to evaluate this from r equal to 1 to r equal to 2. So that's going to give me 2 minus 1 times that constant. 2 minus 1 gives me a 1, and 1 times 1 plus 3 cosine theta gives me a 1 plus 3 cosine theta. I now have to integrate this with respect to theta. So integrating this with respect to theta, the antiderivative of 1, that gives me a theta. The antiderivative cosine gives me a sine. And I need to evaluate this expression from theta equal to pi over 6 to theta equal to pi over 3. When I plug in pi over 3, that gives me pi over 3 plus 3 times the sine of pi over 3, which gives me square root of 3 over 2, minus, when I plug in pi over 6, that gives me pi over 6 plus 3 times the sine of pi over 6 is 1/2. So pi over 3 minus pi over 6. Well, converting this to 6, that's going to be 2 over 6 minus 1 over 6, which gives me a 1 over 6 pi. And then I have 3 square root of 3 minus 3. All of that is over a 2. So the result of that integral is pi over 6 plus 3 times the square root of 3 minus 3, all over 2. So let's interpret what we just did. So we've calculated the integral of the function f of r comma theta equal to 1 plus 3 cosine theta. So if this function here describes some property, like maybe the density of an object or the height above some area over some region, and that object has that region, or we're integrating over that region, and that region is r is between 1 and 2, and theta is between pi over 6 and pi over 3. So if that function has some property, like the density of an object or the height above that region, then adding all those up, we've actually calculated the mass or the volume of an object. So if it's density, we calculate the mass. If that function represents the height above this region, then we've calculated the volume. And here's what this region looks like on the xy plane. Now let's consider the following region. So this is the region inside of a circle of radius 3 in the first quadrant. So with rectangular coordinates, we can describe this region as x goes from 0 to 3 and y goes from 0 up to the square root of 9 minus x squared. So this right here is describing this region in rectangular coordinates. But I can describe the same region using polar coordinates. So in polar coordinates, the radius goes from 0 out to 3. So my radius is going from 0 out to 3, and my angle goes from angle 0 up to angle pi over 2. So this right here is the description in polar coordinates, and this right here is the description in rectangular coordinates. So we can describe that region two different ways. Now sometimes what's going to happen is sometimes regions can be can be easier described in rectangular coordinates. Other times you can describe the region easier in polar coordinates. But in general, if you see a region that looks like it's going in a circular type boundary, then you want to use polar coordinates. For instance, the region in example 1, it would be difficult to describe in rectangular coordinates, but it's easy in polar coordinates. So the region over here, this region here, this would be difficult to describe in rectangular coordinates, but it would be easy to describe in polar coordinates. Alright, so let's take a look at the idea of switching an iterated integral from rectangular coordinates to polar coordinates. So we have an integrated integral, so we're integrating over some two-dimensional region R of some function f of x comma y dA. And your dA represents either a dx dy or a dy dx. So R is some region. So we can convert this to polar coordinates. So our function f of x comma y, what we're going to do is we're going to use the following equations to convert x's and y's into r's and thetas. So x is r cosine theta. So every place where we see an x in that function, we're going to replace that with r cosine theta. And y is equal to r sine theta. So everywhere in that algebraic expression where there's a y, I'm going to replace that with r sine theta. That should be a sine theta down there. Alright, the differential dA in rectangular coordinates is going to become either the dx dy or the dy dx. When we convert that into polar coordinates, that's going to be r times dr d theta. And then finally, we're going to have to write our region R in polar coordinates. So it's going to be alpha less than or equal to theta less than or equal to beta. So alpha and beta are going to be the two endpoints for our angle theta. And then R, sometimes R is going to be endpoints, but sometimes, or endpoints that are numbers, constants, but sometimes R might be some functions that have theta in it. So, that region that we had in example 1, notice my theta goes from angle alpha to angle beta, and my r goes from some inner radius defined by the function g theta to some outer radius that I define by a function h of theta. And in here r is a 1, so g of theta is a 1, and r goes to 2, so h of theta is 2. And then my angles for theta, so alpha here goes from an angle of pi over 6 to an angle of pi over 3. So let's take a look at an example. So let's say we want to evaluate the iterated integral by converting to polar coordinates. So here we have the following. The integral from 0 to 3 of the integral of 0 to the square root of 9 minus x squared, and our function is 3x squared y dy d theta. So we could attempt to integrate this with respect to y, then with respect to x. I have no idea how difficult it would be using those particular coordinates. But let's convert this into polar coordinates. So where we have this 3x squared y, I'm going to replace x with r cosine theta, and I'm going to replace y with r sine theta. So when I do that, that's going to give me 3, well, the x, that's r cosine theta squared. The y is r sine theta. So this gives me 3r squared cosine squared theta times another r sine theta. And then when I simplify that nicely, that gives me a 3r cubed cosine squared times sine. I am going to replace the dA, which in this problem happens to be a dy dx. I'm going to replace dA with r, dr, d theta. So my 3x squared y dy dx, that's going to become 3r cubed cosine squared times sine times another r dr d theta, which simplifies to 3r to the fourth cosine squared theta sine theta dr d theta. I now have to take this region. So that region, which was 0 to 3 along the x, and 0 to the top half of this circle of radius 3. So this is the graph of that particular region. So I need to take this particular region and I need to convert that to polar coordinates. So if I convert that to polar coordinates, well, the polar coordinates that describe this graphed region, the radius r goes from 0 out to 3, and the angle theta goes from angle 0 up to angle pi over 2. So our iterated integral becomes the following. I'm going to integrate from 0 to pi over 2, from 0 to 3, of 3r to the fourth power, cosine squared theta, sine of theta, dr, d theta. Integrating with respect to r, so adding 1 to the exponent, dividing by the new exponent. So I get the integral from 0 to pi over 2 of 3/5 r to the fifth power, cosine squared theta times sine theta, and I have to evaluate this from 0 to 3. So evaluating this from 0 to 3, if I plug in 3 for r, there's my 3/5 times 3 to the fifth power, cosine squared times sine, minus, when I plug in 0, 3/5 times my 0 to the fifth power. Since this is multiplied by 0, all of that's going to go away. So I end up getting the integral from 0 to pi over 2 of 729 over 5 cosine squared theta times sine theta. We are now going to integrate this thing with respect to theta. So to integrate this thing with respect to theta, first thing I'm going to bring out that coefficient, 729 over 5 times the integral from 0 to pi over 2 of cosine squared theta times sine theta. So to integrate this, I'm going to be doing a u substitution. So u is going to equal cosine theta, du is going to be a negative sine theta d theta, and if I solve this for d theta, that gives me d theta is equal to negative du over sine theta. Now my endpoints are going to change as well. So these endpoints where theta is equal to 0 and theta is equal to pi over 2. So those endpoints are going to become the following. When theta is equal to 0, u is cosine theta, so u is going to be cosine of 0, and that gives me 1. So where theta was equal to 0, u is equal to 1. And when I plug in theta equal to pi over 2, this should be a pi over 2. So u is equal to cosine of theta. U is equal to cosine of pi over 2. And the cosine of pi over 2 is 0. So when I do this u substitution, this 0 is going to get converted into a 1. This pi over 2 gets converted into a 0. The cosine squared is going to become a u, or u squared I should say. And this d theta is going to become a negative, so I'm going to pick up a negative sign. I'm going to put the negative on the outside, and I'll have a du over sine theta, and the sine thetas will cancel. So this ends up giving me a negative 729 over 5, the integral from 1 to 0 of u squared du. So integrating this, This gives me negative 729 over 5 times 1/3 u cubed. Evaluating this from 1 to 0, which will give me negative 729 over 5 times 1/3 times 0 cubed, so that's going to be 0, minus a negative 729 over 5 times 1/3 times 1 cubed, which calculates to 243 over 5. So I hope this video has been helpful for you to understand iterated integrals and polar coordinates.